Okay, so the problem states that a voltmeter with an internal resistance of 20 kilo ohms is connected directly across a resistor, short shunt and an ammeter is connected in series. So basically this is the resistor and there is an ammeter connected here. It doesn't say anything about the ammeter, so we are assuming that the ammeter is ideal or close to ideal, and there is some other portion of the circuit which we don't need to know, but what the ammeter's reading is given, that is 4 milliamps, and the voltmeter is connected here like that in parallel, but the voltmeter has an internal resistance. Ideally, if a voltmeter is ideal, its internal resistance is very high, it's almost infinity. Basically we assume when we do circuit solving, we assume that the voltmeter has an infinite resistance internal, so it's an open circuit, but in this case this is not. So non-ideal voltmeter, the model is like this. So we have the parallel resistance which is 20 kilo ohms. Had it been like infinite or like open circuit, then we wouldn't have anything connected. So the significance of this resistance is the current that comes here is supposed to go the, through this resistance, which the R of which we do not know. But since the voltmeter is non-ideal, it will draw some current. If it were ideal, the resistance, internal resistance would be infinite and it wouldn't draw any current. But in this case, it is a finite value and it will draw some current. So we know the voltmeter reading as well, which is 24 volts. And from that, first we need to find the resistor value from just these readings. So we need Ohm's law. We know Ohm's law, R is equal to V over I. So voltmeter reading is 24 volts and ammeter reading is 4 milliamps. The units are not the same. This has to be converted into amps, so we can write 10 to the power minus 3. So this is becoming 24. This one becomes 24 over 4 and times 10 to the power 3. So the unit will be now 6 into 10 to the power 3 ohms, or we can say 6 kilo ohms. So that is the resistance that we are getting just from the reading, and while we calculate from the reading, we assume the voltmeter to be ideal. So what we have assumed here is that all the 4 milliamps goes through the resistance as well, because the voltmeter is not drawing any current, assuming the voltmeter is ideal. So when we calculate from the reading, we assume the voltmeter to be ideal, and that's why we just calculate this way. But now we know that the voltmeter has a finite resistance, not infinite, so it will draw some current. How much current will it draw? We can find from this information. The voltage across here is 24 volts and resistance is 20 kilo ohms. So the current that will go this way, 4 milliamps is coming that way, little bit of that will go this way, and the rest will go that way. So through the resistance. So the current that goes through the voltmeter, we can say I voltmeter, I don't know, volt maybe. That will be again V over R now, again Ohm's law, and V is of course 24 and R is 20 kilo ohms. So 20 kilo ohms is 10 to the power 3 ohms. So we can say 1.2 into 10 to the power minus 3 amps, which is 1.2 milliamps. So that's how it will be, because this is volt, this is kilo ohms, so unit will be milliamps. We can just directly calculate, but yeah, I've just written like that. So that is the current that goes through the voltmeter. If I draw it again here, this is the resistance and that's the voltmeter, and that's the voltmeter's resistance. Maybe I will draw like that. So that's 20 kilo ohms, and this one here, which actually goes through there because this is just the symbol, that is 1.2 milliamps. So pretty significant amount of current, to be honest. 4 milliamps actually goes through to the ammeter, but only the remaining part will go through the resistance. So that is 4 minus 1.2, that's 2.8 milliamps. So much smaller value. Now we will use this information to calculate the actual resistance, because the resistance is actually taking this amount of current, and that is causing the voltage drop to be 24 volts across the resistance. So the value of the resistance will be V, because that is the voltage across V over I, Ohm's law, and the voltage across the resistance is the voltmeter reading, because these two are actually in parallel. They are the same voltage drop. These two resistances are in parallel. The voltmeter's internal resistance is also coming in parallel with the resistance of which value we want to measure, because they are connected in parallel basically. So the voltage drops are the same. So the voltage drop across the resistance is 24 volts, and the current through the resistance is actually 2.8 milliamps. So that gives us 8.57 kilo ohms. So that's much higher. So the error is, this is the actual resistance considering the internal resistance of the voltmeter, and just from the reading is 6. So the margin of error will be this one minus this one divided by this times 100%. So we get almost 30%. I didn't calculate properly, but if you do this calculation, it's almost 30% something. It's pretty high, and we cannot actually calculate the value of the resistance or voltage drop across the resistance of such a high value with this voltmeter. So what happens is, voltmeter comes with a reading, and to measure the voltage drop across a 4 kilo ohms resistance, or when we want to find the value of the resistance and we know that the range is bit high, we need to use a voltmeter that has a much higher internal resistance, because no voltmeter can be actually ideal in that sense, can't have infinite resistance, but it can have a very high resistance compared to this resistance, and that is very significant. So I will just talk about that a little bit. If we have, let's say, if we want to calculate maybe with this voltmeter we could have calculated resistances of few hundred ohms, because then the parallel combination would be much less, so the current that the voltmeter would draw will be much less in that case. So let's say we want to calculate a 1 kilo ohms resistance. So here is 1 kilo ohms, and the voltmeter that is connected across it has an internal resistance of, let's say, 100 kilo ohms. So the current that it will draw now will be much less, because if we apply current divider rule, we know that the current, this is the total current. If you are aware of the current divider rule, I don't know if the current divider rule is known to you, but if not, then I will just talk about like that from here. So let's say this voltage is 10 volts, so 10 over 100 kilo ohms, and this will be 10 over 1. So we can see the ratio will be the current drawn that is here. So this will be the current drawn by the voltmeter, so I volt, and that will be 0.1, whereas this will be 10, and just ratio if we talk about, if the voltage drop is 10 volts. So basically that is the difference is much smaller in this case. So whenever we want to find the value of a resistance or find the value of the voltage drop across a resistance, and if we have some idea of that value, the resistance value, the range it can have, we know it can be couple of hundred or it can be in the kilo ohms range. So we have to select the appropriate voltmeter with higher enough internal resistance so that we get the accurate reading. That's all it is. So yeah.